So this sessions will be recorded and you will have access through the NPTEL portal itself. And then if you want to recall, you can go ahead and view it from there. Apart from that, mostly the sessions will be like on mostly on Tuesdays 6 to 8, and then we will and at the beginning we'll start with the kind of summarizing the week, the corresponding week's videos, and then go ahead with some questions that I will provide, which will be similar kind of from your assignments. So the directly the assignment questions we can't solve. That's basically for you and to evaluate your performance. So we will do some problems which are similar to it. Yeah, so and then at the end we can go ahead solving some doubts if you have. So yeah, you are free to discuss whatever during the course. So feel free to stop me if you want to ask. So it's anyway a kind of you are free to ask, as it is that's the benefit from the live sessions here. So going ahead, what is nanobiophotonics? So you would have seen in the video. So nanobiophotonics being made from basically from interaction of three areas. Yeah. So yeah. So at one arm it's the photonics. Nanotechnology, and then you have biology. Yeah. Or you can also go for like biology, or maybe it's more on engineering, so it's maybe biotechnology. So nanotechnology, biotechnology is you have then this is also biophotonics. Yeah. Here you have areas like nanobiotechnology or bio-nanotechnology. Here we have nanophotonics. So and if this three interacts together, what we essentially say is nanobiophotonics. Yeah. So that's it shows its interdisciplinary nature. Yeah. And then when we go ahead, why we want to study it? Because it finds its applications in a variety of areas. Yeah. We can go for, like, for example, we can use it for diagnostics. Yeah. By making sensitive detection platforms. Go for therapeutics. Yeah. Through nanomedicine, development of nanomedicine, and also light based therapies. So yeah, molecular imaging. So you can go ahead and develop some molecules which can give which can used for cellular imaging. Yeah. That can help in diagnosis, or you can have also maybe biosensing platforms which may involve some nanoparticles, involve photonics concepts. Yeah. Then you have therapeutics, in which you have nanomedicine. Yeah. Which has essentially higher uptake in your body and such characteristics. And then you have some light based therapies. Yeah, that makes it kind of interesting due to its lot of applications. There are far more applications here. So why we do this is something because as we are dealing with mostly on light, so mostly because it is non-invasive, or in some cases minimally invasive. And non-destructive in most cases. Some cases it may be non-destructive to biological materials. Yeah. So, and it has aspects of both fundamental understanding, yeah, to devices. Yeah. And why it becomes interesting is this area, as we are using photonics, makes it faster, because the technology we have to record the photons is faster. We have more sensitive, yeah, using the current methods of current spectroscopies and optical fiber technologies. We can develop more sensitive and less error based devices, and also it is less affected by external factors, by factors. Yeah, factors like temperature, pressure, yeah. So coming to why photonics, because the biological materials that we deal with, yeah, like the tissues, cells, those are quite good to be observed with the photonics, like the visible range, yeah. Lot of the things we can observe through the visible range. We perceive everything in the form of in this range, yeah. We see any object through our eyes in the visible range. Plus the technologies nowadays is such that we can have devices in a like portable form, which we can have, which we can deploy for applications ranging from microscopy to spectroscopy, and even to point of care devices, such that it can be directly deployed in the field. So now the technology of LEDs, yeah, those are something that we can have stable sources for light, and also the photodiodes, which are kind of cheaper sources for detecting the slight changes in the intensities. So why biology is something that I told you. Biology has a very high social relevance, yeah. So there are a lot of issues in the society, like the diseases, upcoming diseases, yeah, like we had COVID, and diseases burden, yeah. Then we have some issues like antimicrobial resistance, Yeah, so those things usually need uh, a nudge from this interdisciplinary areas of research. So we'll go ahead and see some of the so going ahead, we'll see what are the future that we see. Yeah, we need uh, better imaging of cells, the technology that we look ahead. uh, Point of care sensing, then we have theranostics, yeah, therapy plus um, diagnostics, yeah, and then yeah, molecular level imaging. These are some of the areas that people are currently looking ahead at the domain of nanobiophotomics. So we'll go ahead and discuss some of the problems, yeah, and then yeah, I'll give you some time to solve it, and then we can discuss the question answers. So the first is, which of the following applications is associated with nanowave photonics?
Hello, it's
Yeah, so actually it is all of the above. So nanobiophotomics, it has applications and quite a lot of areas, and you can go ahead and explore yourself. So yeah, photodynamic theory is kind of, it says the name, yeah. So it uses some dye to transform light into chemical energy, and that's what is used for uh, I think in some cancers also, because it can specifically uh, target and have cellular destruction. So yeah, but in gene editing uh, and also in stem cell also, it has a lot of applications. So yeah, yeah, you guys can uh, explore and see what all are there. Okay. So which of the following is an example of biophotonics based medical diagnostic technique? So yeah, yeah. One of you has mentioned, yeah, D. So optical coherence tomography is an example of an biophotonics-based medical diagnostic technique. So it is a non-invasive imaging technique that uses light waves to capture high-resolution cross-sectional images of biological tissues. It is so it is commonly used in ophthalmology to examine retina and anterior segment of the eye. So it has also found its application in cardiology and dermatology. Okay, so yeah, OCT is an example. So it's a medical diagnostic technique and it is non-invasive that we mentioned here, which uses light waves to capture high resolution cross-sectional images of biological tissues. So it has found its application in ophthalmology. So it's basically a study of eye. It's to examine a retina and anterior segment of the eye, and cardiology and dermatology. So basically heart and skin also they are exploring. So okay. What is fluorescence microscopy used for in biophotonics? So yeah. So fluorescence is basically a technique in which we we create photons here. So what is its application in biophotonics?
For imaging live cells and tissues.
Okay. Yeah, so fluorescence microscopy, fluorophores or fluorescent molecules absorb light at specific wavelength and then emit light at a longer wavelength. So, so which one will be like longer wavelength, which will have higher energy and which will have less energy? Like it is absorbing light and then emitting light. Which one will have a higher energy?
The light which is absorbed
Okay.
because it's higher in frequency.
Mm-hmm. Yeah. So as we know, hc by lambda is equal to E. Yeah. So it says that absorb light and then emit light at a longer wavelength. So if this increases, yeah, this will decrease. So essentially we get uh, a longer wavelength in a fluorescence, a lower energy photons being emitted. So this emitted fluorescence is used to create high contrast images of biological samples such as live cells and tissues. So yeah, fluorescence microscopy is a nice technique because in which you have so the main thing you guys can go and see is something called as a fluorescence cube. Okay, in microscope there will be a fluorescence cube, which basically is the heart of the microscope. So how it allows the light from to come and then to reflect. That's there will be a filter or a mirror here. How it does is something that you guys can see. So yeah, so that's the concept of fluorescence microscopy. So do you in nature are there any example that you recall in which you are kind of generating or creating any photons that you have seen?
Do you mean bioluminescence?
Yeah, bioluminescence. Yeah, do you know how it happens?
Uh, Fireflies are
Okay.
an example of,
Yeah.
and GFP was discovered from
Hmm.
an extract from uh, uh, a jellyfish.
Yeah, GFP, green fluorescent protein. Yeah.
Yeah, yeah.
So yeah, like fireflies is quite a normal example. So fireflies essentially has one enzyme called as luciferin. Yeah. So luciferin is an enzyme that is there in the fireflies, which is responsible for the uh, for this bioluminescence. So it essentially reacts with the oxygen, and then it gives out so this luciferin, and there is the enzyme that is involved is luciferase. Okay. So when it converts to luciferin, you will get the light which comes down to H2, and then you can observe it through your eyes. So bioluminescence.
Sir, but
Yeah.
can it be considered as an example of fluorescence? Is it same as fluorescence?
Not fluorescence.
No, right?
It's not. It is luminescence.
Yeah.
It's not fluorescence. So it's luminescence. Fluorescence is basically you have to incident it with one light of lambda 1, and then it will generate a photon of lambda 2, which will have energy lower than the lambda 1.
Okay.
Yeah, the photons will
So,
have energy.
is there any examples in the nature that gives fluorescence?
The green fluorescent protein that you told, yeah, that is not luminescence, that is fluorescence actually.
Yeah, but is that instant? Like,
Yeah,
fluorescence should be instant.
yeah. Fluorescence is so there are like 2-3 types of this generation. You have fluorescence, then you have delayed fluorescence, then you have phosphorescence, and then delayed phosphorescence. So it usually depends on the time scales. So that is like you won't it will be in some 10 orders of some seconds. I don't recall what it is, but yeah, it happens when you incident it with the light. There is no delay actually. In the case of fluorescence, there are no delay.
Thank you.
But there are some cases of delayed fluorescence and all that essentially there is one concept called a Jablonski diagram. Okay, if you study, there is something called as Jablonski diagram, in which there are it's a simple energy band gap structure. So you have if I, so basically you will have different energy state. Okay, so you have the ground state, yeah, ground, and then you have different, so you will have some vibrational states itself. Yeah, so this will be ground. So oh my god, that went. Okay, so ground, and then you will have state 1 and then state 2. In this state 1 and state 2, there will be some vibrational states. Yeah, all will have some vibrational states. Okay, then if you are putting light, inserting it light, it can go ahead to any state like this. Okay, and then it can come down, and then it can this is what mostly happens in absorption. Yeah, but then it has another system. Okay, where it can flow down from that system. So there are some called as inter-system crossing. Okay, so in cases of such, you will have delayed, the time will be more delayed. Okay, so here see, here there is, like in absorbance, what happens is you will have so it will be absorbed from here, but here you have an energy change. Yeah, that energy will be coming out as a light. Okay, So you go ahead and see about this Jablonski. It's quite an interesting thing. How a molecule absorbs light and then comes down to its ground state, and how it emits the light.
Okay, sir.
So yeah, next one.
Sir, it is option D, nuclear energy production.
Okay, yeah. So yeah, those are areas, and essentially we will study those during the course. Yeah. So before that, I actually wanted to show the Jablonski thing. Yeah. So I'll see if we have a good. Yeah, I think this one is good. So here it is, yeah. So here you can see the time scales also. So excitation, so a ground state, a molecule in the ground state is at S0 0, and when you incident it with some energy, it goes to S2 state. Yeah. So it takes 10 to the power minus 15 seconds for absorption. Then that light, that molecule can stay in that for some time and then come down to the next state. Yeah. When it comes down to the next state, okay, so that can be considered as internal or vibrational relaxation. So vibration in the molecules, and it can come down. So the energy loss, so the energy can't be created, can't be destroyed. Yeah. So the energy is used in the form of a vibration. Molecules vibrate, yeah, in front like that, and then it will come down. So that because the energy is would be same, so now the energy, one part of energy goes down to the vibration and another comes down as light. So this is the fluorescence that you see. Yeah. So so the energy when it was excited, it was from S0 to S2, but then when it is coming down, it is only coming down to S1 to S0. So it will have their own vibrational states, but essentially it coming to S1 to S0. So the energy has decreased. But then you have other systems here. Here we call as intersystem crossing. When you have intersystem crossing, so the time involved is more, and then that's why you have delayed fluorescence. So those are some those people will have will manipulate the systems in a way that will show phosphorescence, or that will show fluorescence. So depending on your application, you can design your molecules which will give maybe phosphorescence. So something like when your watches, yeah, those watches will glow after the light is incident after it, and long it will and the flow and the glow will be there for long. So there needs a delayed process. It should not be like spontaneous. So there you will have a molecules designed which will go through the intersystem crossing and then come down to the ground state. Okay, cool. I think yeah, I think then it's okay. This we went through. Yeah. So some of the questions are actually taken up from the past previous year questions. So yeah, you can expect similar questions in your exams too.
Visible light, sir.
Why is it so?
Because in photonics, the no other parts of the electromagnetic spectrum is used. Mainly related to biophotonics, these are not used. Like X-rays and gamma rays are ionizing, so they are restricted to the biological tissues or the applications.
Yeah. So yeah, you have covered kind of a lot of things, but yeah. So the benefits, yeah, as you told, it is non-ionizing. And then you have good enough resolution, yeah, high resolution here. So this resolution actually depends on the wavelength of the light used. Then you have fluorophores also available, yeah.
So can you explain the relation with the resolution and wavelength? Like,
so it's
how is
like
it related?
yeah, so the thing is, when we go for so you want to observe something, yeah, so you want to measure a particle, okay, measure any item, so you should have a scale which has marks uh, short than it or in that order, yeah. So you want to measure the diameter of this circle, yeah. So you can't have a bigger scale like this which has marks like this, yeah, and try to measure this diameter, yeah. It's similar with the light. So if you have very small structures, okay, maybe nanoparticles, so you have to have light which is in that order so that it can interact with that material. So it's kind of analogy I'm giving, but for example, it's like we go for so it's similar to that, like you have optical microscopy, but then we have electron microscopy. We go for electron microscopy just because of the resolution.
Yes.
So resolution, so it's like I think it's so you can only go for lambda by 2 resolution. So if you have you have a wavelength of 400 nanometer, you have a light that is 400 nanometer, you can go down and observe structures which are of 200 nanometers. So that's
Yes, sir.
that's a theoretical limit. Practicalities, it's maybe different. So you have fluorophores, availability of fluorophores, and then you have some molecules that has specific absorption and emission absorption, yeah, in this lights, in this visible range. And also you have the normal optics, the lenses and all, which are kind of well designed for the visible light. So yeah, playing with visible light is something that is easier, yeah. Okay, so green light of wavelength 500 nanometer carries energy of how to do it.
No idea, sir.
I gave that formula a bit ago, yeah, on connecting the wavelength and energy. Nope. Okay, so I told you E equal to hc by lambda. So value of h, c, and lambda we don't know, lambda is given 500 nanometer. So what is h? H is also called as Planck's constant, yeah. So its value is 6.626 into 10 to the power minus 34 joule seconds. Can you all try? What? Why to open? I'll tell sir. Gone. I'll tell sir. I can't. Done. Gone. Pura gone. Hmm? Okay, should we go ahead and solve? You all are trying, or? So yeah, what we are getting, E equal to 6.626 into 10 to the power minus 34 into 3 into 10 to the power 8, yeah, and 500 nanometer we have to convert it into meters. So 500 into 10 to the power minus 9, yeah. How much you will get? 3.98 into 10 to the power minus 19 joules we got. Okay, so but we have to convert it into electron volt. Okay, so 1 electron volt is equal to 1.602 into 10 to the power minus 19 joules. Okay, so the energy we will get is 3.98 into 10 to the power minus 19 joule divided by 1.602 into 10 to the power minus 19 joule. Yeah. Yeah, so it's coming 2.48 electron volt. It's easy to follow.
It's understandable.
Understandable, yeah. Okay, cool. So yeah, if it comes any relation on wavelength and energy, you can go ahead and use this formula, or you can also use its other formula, E equal to h nu. So if frequency is given, so you can go and put in h nu. So yeah, so you can end up in energy, and then so just for your thing is you remember some of the constant like speed of light, because obviously you are studying the nanoBiophotonics course, so should know the speed of light, and Planck's constant is something that will be very much used, so you can try to remember. Mostly it will be given in your questions, but yeah, you can remember it. Yeah. എന്നെ ഏട്ടപ്പം ന്യൂമറിക്കലി ചില താറാണ് BTech students are Diana Krish.
It measures the intensity of light?
Yeah. So yeah, it measures the intensity of light. In biophotonics, a photodetector is an essential component. It is used to measure the intensity of light. So when light interacts with the biological samples of or tissues, it produces signals that contain valuable information about samples' characteristics or behavior. Photodetectors are designed to detect and convert these optical signals into electrical signals, which can be further processed and analyzed. Yeah. Okay. So yeah, we had a question on optical coherence tomography. So here comes like what is its application, or what is its purpose?
To image the internal structures of biological tissues.
Yeah. So OCT is used is a non-invasive imaging technique that uses light to obtain high resolution cross-sectional images of biological tissues, and as we had told, it is used commonly in ophthalmology and other medical fields. So yeah, so Consider a photodiode that has a band gap energy of 1.43 electron volt at 300 Kelvin. What is the cutoff wavelength for this device?
So we weren't taught about this, I think. Like about band gap energy, we don't know. Cutoff
Try.
wavelength, we are unaware.
Yeah, but
Photodiode also.
okay. Yeah, maybe that and all are, but you try to see. Yeah, it's the concepts are easy actually. So try if you can. Otherwise, anyway, we'll discuss. So you try, and the concepts are kind of easy on the easier side. So you can try. Anyway, we will discuss it. Don't know. So the cutoff wavelength is basically the longest wavelength of light that can be absorbed to generate electron hole pairs. Okay, that's the longest, that's the cutoff wavelength. So to calculate it, like, it's the same formula, yeah, that I told, E equal to hc by lambda. So yeah, you can try starting with this, and then maybe you can end up. Maybe the first step is maybe to convert this electron volt to joule and put in this formula. Are you trying? Or should I
Yes,
go
sir.
ahead?
Yes. Yes.
Yeah. Okay. Okay, we'll try.
I'll try.
You're done taking spectra? You're done?
Sorry, I don't know if it's right. I got something like 8.68 into 10 raised to minus 7 joules.
Yep. On to something?
Yes, I got like 8.68 into 10 raised to minus joules.
Eight.
So I have to convert it.
So you got? Okay. Okay. Okay, yeah. You end up in the, yeah, in nanometer basically. Yeah. Yeah, got the value?
The value I got was 8.68 into 10 raised to minus 7.
In nanometer, can you convert? Is it in meter?
Pardon me, sir.
Is it in meter or the wavelength? No idea, yeah? Okay, cool.
Yeah.
We'll do it, yeah. So, yeah. So first what we'll do is we'll convert the 1.43 electron volt to joule. Yeah. So how you did it? 1 electron volt is actually 1.6 into 602 into 10 to the power minus 19 joules. Yeah. So 1.43 will be 1.43 into 1.602 to 10 to the power minus 19 joule. Yeah. How
Yes.
much you got?
2.29 into 10 raised to
2.9 into
2.29.
okay. 2.29 into 10 to the power minus 19.
Yeah.
Okay. Joule. Cool. So okay. Now what will you do is we'll put it in this formula equal to hc by lambda. Yeah, h is again 6.626 into 10 to the power minus 34 into 3 into 10 to the power 8 meter per second, and then okay, lambda is something we have to take out, so this is the E. Cool. So lambda equal to 6.626 into 10 to the power minus 34 into 3 into 10 to the power 8 divided by 2.29 into 10 to the power minus 19. So you got this, yeah?
Yes, sir.
Okay, then how much you got? This value?
8.68.
8.68 into
10 raised to minus 7. I think so.
okay,
Not sure.
meter. Yeah, this will be in meter. Okay, because we took 3 into 10 to the power 8 meter per second. Yeah. So So we have to convert it into maybe nanometer. So 1 nanometer is equal to 10 to the
10
power
raised to
minus
8.
9 meter. Okay. So okay, so basically 1 meter is 10 to the power 9 nanometer. Yeah, so we'll basically multiply it 10 to the power minus 10 to the power 9. Yeah, so what we get is 868 nanometer. Cool.
Okay, sir.
Yeah, nice.
Hmm.
So yeah, I don't have a yeah, so I followed your calculations. I don't have a answer to, but yeah, that's what you will do it. Okay, cool. Should we go to the next one?
Yes, sir. Why was the Kelvin, the temperature given in the question? Just to confuse us?
Yeah, but the thing is, band gap energy usually has a relation with temperature, but yeah, you don't have a
We don't
uh,
need to use that
no
equation.
need to use it. Yeah, yeah. So a point source of light is 12 centimeter below the surface of a large body of water. So the refractive index is given. Uh, of water is given. Now, what is the radius of the largest circle on the water surface through which the light can emerge from the water into air? So, yeah, you know about refractive index?
Yes, sir.
Okay, then try then solve it. Yeah, it's kind of more on optics plus like optics plus geometry. Yeah, more on that. Yeah, then you will need something called as a Snell's law. Yeah.
Okay.
So, are you aware of it?
I've heard of it.
Okay. Yeah, you can search it. No issue. You are.
Okay.
Yeah. Take your time. Solve it. Try to draw the thing and.
So, but using Snell's law, we need the theta angle to
Yeah.
calculate, right?
So you have a condition. Yeah. What is largest
Angle
circle?
of incidence and
Yeah. That's what. Yeah. That's what I. Yeah. You will have that. That's what I told. Yeah. It's question of geometry too. So yeah. Okay. You lined up on something? So yeah, let's draw it first. This is the surface of a large body of water. So this is the surface, and then you have a light source which is 12 centimeter. Okay, just 12 centimeter. So what is the radius of the largest circle on the water surface through which the light can emerge from the water into air? So yeah, you can have multiple things, yeah, multiple rays, but the largest will be which will have a critical angle, yeah. You know about TIR, yeah, total internal reflection, yeah.
Yes, yes.
So one of them will be like this, yeah, that condition, yeah. So it's like this. So if you put a normal, yeah, so this you can consider theta, yeah. So this will be theta, and this will be 90 degrees, sorry, Celsius, yeah. Maybe now you can try solving it. So basically you need this distance, yeah, this R you need. This is the circle.
So sir, I don't think I would be able to figure it out. Like the theta angle still, I don't know how to find it.
Okay. So Snell's law, yeah, we're talking. So Snell's law, yeah, I was mentioning. So it basically tells n1 sine theta 1 equal to n2 sine theta 2. Yeah. So here in case of n water, yeah, nw to sine theta, yeah, equal to n air, okay, and sine 90. So sine 90 is, sorry, so sine theta, this is critical angle basically. So sine theta c equal to, so we will consider theta c. Yeah. Sine 90 is 1, so n air by n water, which is n air is 1.33. So this will come out as and then theta c you can take it as sine inverse 1.133. So can you calculate this value, theta sine inverse 1 by 1.33?
The average height factor taken what 0.96 under the 0.96
আমি greater than 0.96 লিখে রেখেছি ক্যালকুলেট করেছি ওকে greater than 0.96 লিখে রেখেছি ওটা ইউজ করে রেখেছি
What is the value? Hello.
0.85 radian.
In degrees? Degrees?
48
48.
points. Yeah.
48.75.
75.
Okay, then you can. I don't know why. Sorry. 48.75 degrees. Okay. Okay. Then if you have this one as 48.75, so this will also be 48.75. Yeah.
Yes.
Parallel angles. Yeah. From parallel lines basically. Then what we'll have is this is 12. Okay, so you need this. So what you will use is tan theta. Yeah, you can use tan theta equal to
Sine by cos.
Hmm?
Sine theta by cos theta. I'm sorry, sir. I'm from a biology background, so after plus 2 I haven't touched maths.
So tan theta will be equal to so this is the right angle. Yeah, so you have a right angle in this theta. Yeah, this is 12 and you need to find this r. So tan theta equal to r by 12. Yeah, height by the base or whatever it is. So yeah, find out this one. Tan theta you find out and then basically r equal to 12 into tan theta. So here theta will be 48.75. How much it is coming? For me it is coming as 13 point, so 12 into tan 48.75.
Sir, 13.69.
It is coming around 1.14, so it is coming so yeah, it is coming something around so I am not able to, yeah, it is coming around into 12 if I do, it is coming around 13.68, yeah, centimeter. So 13.68 centimeter is the largest circle onto the water surface through which light can emerge from the water. So yeah, that's all we had. Yeah, any doubts, questions you have, then we can discuss. No? Okay, then we will close the session. We will meet again next week, same time.
Okay, sir. Thank you.
Okay, cool.